Yes, so thank you everyone for being here, and thank you to Lorenzo and all the organizers for the kind invitation. My name is Shammah. I am a CTO at Untitled Fund, which is a non-profit that I will introduce to all of you. And I'm here to speak about some work that we have been doing and we keep doing, focusing on quantum error mitigation. I'm also visiting scientist at RIKEN, Japan National Lab, and at the University of Milan. So, and hi everyone also online, both here and online, please feel free to interrupt if you have any question. So this is the outline of today's talk, and I will give a brief introduction to noise in quantum computing, also given the diverse and broad background that I see here from the audience and the students. Hopefully a motivation and a brief overview of quantum error mitigation techniques. And then we will zoom in into one specific technique, zero noise extrapolation, which will also be the subject of the hands-on exercise that will be led by Andrea Mari this afternoon. I will also briefly mention Unitary Fund's broad activities, also given the fact that we are quite a unique player in SQMS, and also the role we play with respect to SQMS effort to sustain and support open source software. And then I will conclude. So once again, this talk is very much connected to the hands-on lab that this afternoon, but also to the talk that will follow by Ryan LaRose. And also I take the opportunity, I will introduce more generally the team, but I also want to acknowledge my team members here, Nate, Misty, Ryan, and Andrea. And we will also help you out this afternoon with hands-on exercises, also for folks online. So, yes, that was the introduction, but here I have a fun slide, and I wanted to ask here in the room if anyone besides Lorenzo knows what this image is about. Maybe besides Lorenzo and Andrea. Anyone? It's too old, probably. So this is the Programma 101 by Olivetti, and it's a personal desktop programmable calculator, by some considered the first commercial personal computer. And it was designed, invented, and commercialized in Italy, presented in 1965 at a fair in New York, designed by a famous designer, even if it looks quite old by today's standards. But unfortunately, maybe most of you don't know about Olivetti, this Italian company, because they didn't really believe into electronics at the time. And so this was really a pioneering example of what then became mainstream personal computers almost 15 years later. Why am I talking about this in a talk about quantum error mitigation and quantum computers? Well, it doesn't have a screen. It's hard to code. It has a limited computing capability. It has a limited instruction set. It was at the time enthusiastically adopted by research centers such as NASA and Los Alamos National Lab. And by those days standards, it was quite expensive. So I guess some of you can find some comparison with today's quantum computers. Although I think that this is not a very correct comparison, because broadly speaking, today's quantum computers look more like the very first attempts to perform calculations with these very big machines. This is in particular is Colossus. It's one of the projects from Second World War. There are very few available online. They're still generally quite bulky, or even if the microchip is very small, generally the control room, it takes quite a bit of a size, and they require really expert operators. But even then, I think the comparison is not very accurate, because at the same time, today's so-called noisy intermediate scale quantum computing devices, NISQ, this is this acronym that was coined by John Preskill. They are connected to the cloud. They work with a state-of-the-art open source software and infrastructure, and they leverage a quite modern user experience, user interface stack. So really current NISQ devices are a mix of many things, plus one thing that neither of those two devices that I show from the history of computing were experiencing, which is very high level of noise and hence errors in their hardware. So that's where we're starting with this talk. And now we will move to error mitigation, which is reducing the impact of this noise with respect to errors that affect calculations. So what does it mean today to run a program on a quantum computer or a simulator of a real device? Well, from the lectures that have preceded today's session, we learned quite a bit about the general overview and also the state of the art of hybrid quantum algorithms, such as the variational quantum algorithms. So there is a mix of classical computation and quantum computation. But for the purpose of this talk, well, less generally, but in a simpler way, we can really focus on what is one of the simplest forms that a quantum program can take, which is a quantum circuit. So it's stuff that basically was designed and thought more than 20 years ago. So let's imagine that you have your very simple quantum program, which is represented by a quantum circuit. Here it's just 2 qubits and 2 gates acting on them. Well, nowadays, due to the infrastructure that I briefly mentioned, through the cloud, you can connect to a quantum computer or to a Lego version of that, up to you. Then, always through the cloud, the quantum computer will receive a job, execute the instruction that you've given, and you will obtain, as a readout, a series of bit strings with each bit correspond to the state of a measured qubit. Here we're assuming that you have quite a bit of qubits. And then due to the probabilistic nature of these devices and quantum mechanics in general, you will have to average out your result many times, at least because of the nature of the quantum algorithms that we are running on these devices. And so you will have several runs. So far, we're still in the ideal case. Actually, we are leveraging on today's infrastructure to be able to connect from the cloud, even from here, with these very delicate machines. So I will have just a few images, equations in this talk. This is basically one of them, on which I will develop briefly. How can we picture what is happening on the quantum computer? So in the simplest terms, what we can think of is that we have evolution of a quantum state. And this happens through unitary operations, to which we have, of course, to add at the end the measurement that is not linear. And if you add some barriers, so if you do some manipulation on the qubits, even in the simplest quantum circuit model, then this is not completely the case. But for most part, that is what happens when we perform a quantum circuit idealized evolution of a system. And here in this notation, I'm using the density matrix formalism. Here there is a time evolution. So this is basically the von Neumann master equation, which is just the statistical version in terms of density matrices of the state evolution given by Schrödinger equation. So far, so good. Everything is unitary. We have actually a Hamiltonian that is time dependent, that is applied to the system. And here I set h bar equal to 1 because that's what quantum physicists like to do. But we all know that if you wait long enough, namely if your quantum circuit is too deep, at some point, the result that you will obtain, it will be inevitably be very noisy. Actually, maybe in the best case, it will be like some sort of white noise, washing out any sort of previous computation that you've tried to apply. Namely, all your qubits will go to the ground state. And why is that? Well, the reason is, of course, decoherence. And Davide Venturelli very nicely provided an overview of existing processors, architectures, and platforms, and also mentioned that we have at our disposal this very broad set of devices because at the core, they're all governed by quantum mechanics. So here is a very simplified picture of what happens in a quantum processor. Don't worry about the fact that most QPUs, quantum processor units that are available online are on superconducting circuits or maybe on ions, atoms. Most generally, what is called the quantum optics approach is enough to try to understand in very simple level, at a very simple level, what is happening on the quantum computer. So, and generally this quantum optics approach is that of cavity quantum electrodynamics. So we have a qubit that can be in the ground state or in excited state, which is interacting through a cavity or could be some connection operated also by outside, but then it also has some leaks. So it has a coherence time that is internally assigned to the qubit, and then there is also some leak here, kappa, not only gamma, but also kappa, that is provided by the fact that this cavity is not perfect. Add to this the fact, as I was mentioning, that we would like to operate on these devices. So we want to have a time-dependent picture. So at the same time, we want this to be isolated, but when we like to apply an operation, we want to be able to, let's say, open the box. And this is at the core of all problems that we are facing with quantum computing devices, and we will continue to face. And basically, in this case, this is a very simple example. Generally, you have Rabi oscillations that can continue basically forever. But what people see in the lab in this simple experiment, but also when you calibrate and characterize the T1 lifetime and T2 lifetime of your qubit, you see that basically these oscillations fade out just because the coherence time is limited by hardware specifics. Okay, this is a very simplified approach to noise. Can we say something more? In the end, we've been playing with quantum optics in the lab and now also in more complex devices for quite some time now. So there is definitely decoherence noise, which is a typical quantum noise in the model that I've shown you. But there is also control noise due to the fact that we want to continuously operate on the qubit. So what is by physics a static Hamiltonian is actually a time-dependent Hamiltonian. From a theoretical point of view, this makes things in terms of modeling the system even more complex. And what could happen? Well, here you see the block sphere that has already been introduced in the school, but basically it's a way to represent a quantum qubit with its coherence. And you see that, for example, we would like to apply a perfect sigma z rotation on the qubit, but actually due to some issues in the device, we're applying an imperfect control, which is here shown by this other trajectory. And there is also another component in the Hamiltonian that we are applying. So this is also grasped here by the fact that we may have an idea or ideal Hamiltonian, but then we also have a noisy part. There's also noise on the pulse shape. This, as I was mentioning, we have a quantum circuit ideal visualization of the algorithm of a quantum circuit, but then of course these controls are converted at the pulse level, discrete or continuous, up to you, up to the level you want to model them. But basically you will have some pulses being applied on some qubit. And there can be some pulse shape noise. This could be, for example, problems in the lasers that are operating on the Rydberg atoms, in one of examples. This can be classical or quantum. Then we have crosstalk noise. This is particularly important in artificial atoms in solid state, such as superconducting circuits. And this means that neighboring quantum qubits or artificial atoms are not as isolated as we would like to from each other. So when we operate on one, we're actually also affecting the other ones. And in this case, this is an idealized view of a line of atoms or ions, excited atoms on which a laser pulse is impinging on, that is also having effects on neighboring qubits. And then we could have, for example, things such as the leakage noise. So we're always speaking about qubits because that's the simplest sort of like representation of these systems, that it's fairly good. But let's not forget, as it was also introduced in the first talk of this school, that many of these devices, including atoms, they have many excited levels. And this is particularly true also for artificial atoms, which can be modeled as nonlinear oscillators. So there's always the chance that you end up in some, could even be like an intermediate state or virtual state that is not just the 0-1 computational basis that you like your qubit to be confined to. So as you see, there is a lot of noise and noise sources, and this can affect, and this affects the quality of the computations because it destroys coherence. So this is a more refined slide about the fact that there are different ways to represent this noise. We did mention most cases. There are some assumptions that are usually made in quantum computing, such that noise is usually independent among qubits, seems fair, and that usually noise can be simulated with some action after a perfect gate is applied. So you could think of some depolarizing channel or some other gate that is applied after your perfect gate. But let's also not forget that the picture could be a bit more complex. Noise can be correlated. To some extent, crosstalk is a sort of correlated noise, but both in time and space. And ideal operations such as perfect gates and noise may not be separable. So for example, we may need a super operator picture to describe what is happening in the system. And we can not only use the Hamiltonian formalism. So there are a variety of tools that are available nowadays to help us out in simulating noise devices and studying them. And during this talk, I will continuously make reference to existing software tools. And this is just one of them on which I've been worked on, which is a QTIP QIP. QTIP is a quantum toolbox in Python, and QIP is a module that has been spun out and is a new package for quantum information processing that allows to go from what maybe most of you may be familiar, at least by this time, given this summer school, like the quantum circuit formalism, to something that is more similar to the actual continuous pulse level instructions that are applied on a typical quantum device. So this is a tool to simulate any kind of quantum processing unit that you can hard code from scratch or based from models that are present in this software package. As I mentioned, also speaking about pulse level simulation and control, because generally then I will switch to the more simplified picture of gate level simulation of instructions and also generally also of noise. There is now an ecosystem of tools that allows to simulate specific quantum processing units. So one of them is a pulsar that has also been mentioned earlier in this summer school, which is specific to the quantum processing unit characteristics of cold atoms, Rydberg atoms, and is mainly developed by Pascal, a startup in France. There is also a new tool, not in Python, but in Julia, called Blockade. It has a reference to the Rydberg blockade that allows to address the specific qubits, which allows, for example, here it's a bit small, but you can see that you can basically define any sort of lattice composition. And this is a very big difference to the hard-coded topology architecture that you have in most of other devices. This is something quite specific of Rydberg atoms. The fact that basically, actually at each computation, you can actually rearrange the quantum processing unit architecture and connectivity. Any questions up to now? It's good to have some questions. Also because this way I can drink some water. At least one question, come on. Yes, please. Sorry, I didn't hear. So the question is, when did they start building Pulsar? It's about a couple of years ago, and it's been open sourced in 2021. And actually, we're proud that as Unitary Fund, we had this code to be open source for a reason that we will mention later, because we think that we're still at a very early stage in which these tools need to be open source, because we need to check and improve the quality of existing software infrastructure. Yeah, sorry. And this is a very high-level overview of what's available. On the Unitary Fund YouTube channel, we have dive-ins on these specific tools from actually the maintainers, the developers who built these features. So for QTPKP, there's a 1 hour long lecture. For PyGSTI, which is a more advanced tool to characterize qubit noise with gate set tomography, which is something I will not speak about, but it's, let's say, a more advanced qubit level or gate level tool for characterization, verification, and control. Kenny Rudinger and Eric Nielsen gave a talk, and about Pulsar, Loïc Henriet, City of Pascal, also gave a very detailed talk. So if you're interested, please dive into this Unitary Fund YouTube channel series. So to summarize this first section of the talk, we learned or refreshed the fact that quantum computation is basically quantum evolution with operations that needs to be applied externally, so the quantum state cannot simply evolve spontaneously, but we keep interacting with it. And then we have some measurement. Quantum noise and also generally classical noise introduce some errors in the computation due to decoherence. Different quantum systems, also called now with a fancy name of quantum processing units, similar to CPU, suffer from different noise sources. So one should, to some extent, know what is the noise source of a specific device that one is simulating or using, and that different noise models can be employed, and also tools for characterization. So now there is an ecosystem of software stack, such as Pigsty, that allow to simulate this noise. Let me go back to the basic Schrödinger equation in density matrix formalism. And let me add here a very simple term that we will use later on, but is sort of like a preview of the way that we can simulate noise by adding linearly a noise operator to our equation here. And here is a noise scale factor that, for example, could be a dimensional real number. So this is sort of like a generalization of a von Neumann equation. And for example, it could be a Markovian master equation, which means that with those assumptions, noise correlations are to some extent simplified, because there is no time correlations or like memory in the larger buff that is producing noise. So when excitations escape from the system, they're gone forever. So we spoke about the simulation, but what can we do, and what is the state of the art really empirically, quantitatively, with a current state of current devices? So this is a Scientific American article that I found very well written, which is entitled "How to Fix Quantum Computing Bugs," and it has a very holistic approach to the problem, and also explaining also very recent advancements of state-of-the-art techniques in quantum error correction and quantum error mitigation. So I really point you to this article if you want to have a broader picture also with respect to quantum error correction, which, by the way, will be also the topic of the next lecture. But yes, what can we do to reduce the impact of noise in current quantum devices? And here, let me introduce and give a further motivation for quantum error mitigation. So I mentioned a couple of times now quantum error correction. And this is a sort of like introductory slide to sort of like differentiate what quantum error correction, definitely more popular and more established, is, and what do we mean by quantum error mitigation. So so-called standard quantum error correction assumes that we're encoding logical qubits into many physical qubits, and that there are intermediate measurements for syndrome detection. And that means that correction operations are based on the measured syndrome. So there's sort of like a feedback loop that needs to be to occur in this standard quantum error correction to be able to correct the errors. So this approach is very ingenious. It plays with symmetries of quantum mechanics, and it's definitely scalable, but right now it's unfeasible with near-term quantum computers. What I mean here, so this is a very active field of research, is just that right now, if from the cloud you want to access a quantum computer, you're not able to implement a quantum error correction strategy, not just right now. So what can you do as a user that is not maybe deeply involved in pushing forward the field of quantum error correction, but you just want to have a better result of a quantum computing simulation, quantum simulation or quantum computation? Because, for example, you may be interested in doing some quantum field theory simulation on a quantum computer. Well, you can apply a more approximate set of techniques that have now taken the general term of quantum error mitigation. It's also important to mention that these approaches sometimes under the name of approximate quantum error corrections. And some of the key ideas have been around for quite some time. But let's say that there's been sort of like an explosion recently of these approaches and research direction in quantum error mitigation. So we assume that we can perform multiple and different noisy quantum computations. So we launch many programs or quantum circuits, which are different. Otherwise, we're just averaging out the same result. We collect the result, and then we infer ideal expectation values from the noisy data. So you see that in this case, in quantum error mitigation, the process is quite well defined into two steps. One that is a sort of like quantum sampling of that also serves the purpose generally of learning more about the noise landscape, so to say, of your device. Also with respect to the computation that you are trying to perform. And then a second part that generally, or let's say not generally, but in the simplest term, is just a classical part that is about inferring a better expectation value with respect to the single results that you get, either by single runs or by averages of a single specific quantum circuits. So these approaches are, for most cases, asymptotically unscalable, but feasible with near-term quantum computers. So this means that you can apply these techniques right now also from your laptop. And this is something that at the simulator level, you will do this afternoon. But if you want to connect to a real device, you can also try out yourself what happens. This is part of the story. And then there is also, and this is also sort of like different sort of camps or fields of the NISQ era or leapfrogging this NISQ era. We already need fault tolerance and QC. Why spend time on variational quantum algorithm? So the debate is open. There's a lot of research in this direction, and I will not focus on the results that can be obtained with variational quantum algorithm. But let me mention that these two approaches are not so disconnected. So there is now growing research interest in thinking about quantum error mitigation as a tool for quantum error correction. So as a tool to lower the thresholds that actually forbid right now to be able to implement quantum error correction techniques. And this is, for example, a paper in which one quantum error mitigation technique is used to apply an approximate gate that is important to have a universal set of gates and implement quantum error correction. And it's applied specifically to a gate that brings most of the overhead, of the computational overhead, or maybe not only computational overhead, but quantum resource overhead that implies the quantum error correction calculation. So this is an example of how quantum error mitigation can be used to implement an approximate version of quantum error correction techniques. And talking about popular science articles, this is another article, always from IBM Research, that is very informative from the IBM Research blog, that also sort of like gives an overview into this direction. So you can find it if you go on the IBM Research blog. So let's go back to like a user perspective of using this quantum computer. So generally, as we mentioned, you have a quantum program, you execute on a backend, and then you collect an expectation value. And in this framework, the division of sampling and inference that characterize most quantum error mitigation techniques at the highest level can be split in these two stages. It's really a workflow in which we generate a series of noise scaled or probabilistically sampled quantum circuits. we send them all to a backend, then we collect the many results and we perform some fitting and inference to obtain an error mitigated expectation value. So all the techniques I will speak about, well, most of the techniques I will speak about only work into this framework. And when you are interested in calculating expectation values, such as invariational quantum algorithm. So as you can see here, we generally have overhead in quantum error mitigation in the fact that we have to increase the number of programs that need to be sent to the hardware, and also then we have some overhead in the inference part. But basically, this is the biggest bottleneck that you can see from this slide. Yeah, something was wrong with the transition, but basically I introduced broadly at a high level quantum error mitigation, and I also wanted to place it into a more general context. We spoke briefly earlier about open quantum systems. That's what we mean when we speak about noise. We have like a closed system that then becomes open because of interaction with a bigger environment that introduces noise. There is quantum error correction, which is connected to quantum error mitigation. I did mention briefly that quantum error mitigation is also connected to the characterization of noise and also verification and validation of noise. So PIGSTY is one of those tools. And then there is a more, variational quantum algorithms are deeply related to quantum error mitigation. This is what quantum error mitigation is mostly applied to improve the performance of variational quantum algorithms. And another side that it's more connected to pulse level description is quantum optimal control, that generally I will not cover here, which is the fact that you can improve, generally you can try to improve at least the performance of your device by tailoring how the pulse and instructions need to look like through some optimal control theory open or feedback loop that characterize how you should apply your CNOT gate, for example, your native gate, based on the issues and noise landscape that you have in your device. So this is more general quantum optimal control, but it also requires some feedback, and it's connected to quantum error mitigation. But quantum error mitigation techniques that I will speak about generally can also be pictured at the gate level. So you don't need this tailor of the pulse to be sort of like optimized for your device. Okay, there's something with the transition that I get with slides. Okay, so this was like kind of like a long introduction. Now let's try to look at some of these existing techniques. And there's many. I need to point out this is like a non-exhaustive list. And there will be some references, but there's many more because, as I said, this is like a very active field of research. So I will speak about zero noise extrapolation, and briefly mention also other techniques. So let's give key features of each of these techniques, and then you can dive in the references that I will provide if you're interested in learning more. So zero noise extrapolation, which we will focus on later on, so I will not spend too much time, and also in the example, is a technique whose key feature is noise scaling. So it's a bit counterintuitive, but in order to infer a zero noise value or lower noise value, which you cannot access experimentally, what you do, you worsen the state of a situation. You send a program or apply some operations, such as they're shown here, with what is called pulse stretching. So this is the same circuit, it has the same logic, but it has a longer application time, control time, in order to obtain a result that is worse than the original one. And why do you do that? Again, because what you're doing, you're basically sampling into a phase space that is dependent on noise, so that assuming that you're able to tell what is a lower or higher noise level, then you can basically fit and extrapolate a zero noise level value, expectation value. So this is the key idea behind zero noise extrapolation. We will spend more time on it. And it's one of the simplest techniques that can be applied. The second set of techniques, it's called probabilistic error cancellation, or more generally, it has a quasi-probabilistic representation in the name or in the papers. Actually is applied not at the level of full quantum circuit, but also at the level of a single gate. And the key feature is this. You generally assume that there is a, maybe I should do it here so that it's also online. So you assume that there is an ideal unitary, as we mentioned, which is a set of ideal unitaries, which are these gates applied consecutively in the quantum circuit. Now, as we mentioned, there is different ways to model noise, but one of them, quite simple, is to say, well, we're not really applying these ideal gates, we're applying something else in reality. We're applying some noisy operations. What we can do is that we can decompose, this is just linear algebra, the ideal gate into a basis of the noisy gates with some coefficient. And this is the key of the trick, because then you try to sample this basis and infer the ideal gate. This is the key concept behind the probabilistic error cancellation. As you can already tell, this needs to be done either for all gates or for the most noisy gates. And so it has quite an overhead compared to zero noise extrapolation in terms of the characterization part of this noisy representation. Then there is a set of techniques that I'm calling here, well, these are quite well defined in the literature. These learning-based methods, it's sort of like my way of summarizing the techniques. Well, they are learning-based methods. And what do I mean? Here I'm providing an example with one technique that is known as Clifford data regression, which operates as follows. And it's sort of like an example that can be used also for the other techniques. So imagine that you have your quantum device, but you also have a powerful classical computer. Of course, what you want to calculate on the quantum device should be impossible to calculate, or hardly possible to calculate on the classical computer. Otherwise, you would not use the quantum computer. So what you can do, though, is you can take your quantum circuit, your original quantum circuit, and you can simplify it. There is some theorem that shows that if quantum circuits have a given subset of gates, Clifford gates, they can be efficiently simulated on a classical simulator, so on a non-quantum computer. So the first step you do is you generate some training data based on your original hard problem. You transform your problem into a simpler problem from the point of view of a classical simulation. And then you send these circuits to a noisy simulator, if you have a noise model on your classical computer, or to the actual quantum computer. And in this way, you generate, as it's said here, some training data to be able to learn how to correct with a simple linear model your exact expected result with respect to the noisy result that you obtain either from the classical simulation or sending the quantum circuits to the noisy computer. And then you use this noise model and correction model, mitigation model, to then predict what happens when you run the actual hard quantum circuit on the actual device. So this is an example of these learning methods. And generally, you see there is like some learning part, and this part, specifically this part, is completely classical. So generally, you can do some very simple linear regression, or you could employ some more advanced machine learning or generally inference techniques. Okay, so there's other two, broadly speaking, techniques I'd like to briefly touch upon. The first one is a symmetry-based techniques. And they go through many names because everyone in this field right now, it's coming up with new names. So symmetry verification, subspace expansion, symmetry expansion, and so on and so forth. But they have a key feature, which is that the noisy state, which is the result of evolution in the quantum computation, is sort of like reprojected into a smaller space, let's call it the Hilbert space, that is the correct computational subspace. So here there is some equation. So let's assume that your ideal state psi with this cat is actually an eigenstate of this operator M of S. S here counts for the fact that you can have, it has some symmetry. Then if you measure a basis of these operators onto the noisy state rho, basically what you're doing is something like this. This is a basic, is it, I don't remember any, Born or Born-Hammar representation. But basically what you obtain is actually here, it's a projection that is renormalized by the trace of your noisy state as a symmetrized noisy state. So basically what you're doing is you have your state that has leaked out from the correct computational basis, and then you push it back in the correct space. And this idea basically it's at the core of most or like standard quantum error correction techniques. The difference here is that you don't do it like you don't employ it at the quantum mechanical level, but you sort of like employ it generally at the post-processing level. So you can do it sometimes during the computation by measurement, which is different from quantum error correction because there you simply use the symmetry of operators, or you just do some sort of like post-processing based on symmetries that are not present in the readout of the bit strings that you know that due to the symmetry of the problem, they should contain. So these symmetry-based techniques, I'm also using this term also to include some sort of like symmetry-based post-processing. Then there is dynamical decoupling and randomized compiling. Especially dynamical decoupling is a much older technique. It has actually been developed in the context of nuclear magnetic resonance, because it's a very effective way that you can use to basically keep your qubits or quantum system busy instead of keeping it idle there when you're not using it. And so this idea that actually, I don't think it's even called dynamical decoupling, has been ported to the quantum information setting, actually I think by one of the PIs of SQMS, Lorenzo Viola and collaborators. And it's actually a compiling technique. So it doesn't have any inference. And you can see it exemplified here. It's a bit small, but basically here, so these are two images. I'm gonna focus on the first image, which is about dynamical decoupling. So here you have several qubits, and then you have some gates that are applied to the qubits. And here with these rectangles in purple, you see that there are some sequences, X, Y, X, Y, X, Y, X, Y, and so on and so forth, or here also with an identity. And these are sequences that were not present in the original quantum circuit, but which are added in order to keep the qubit busy and less prone to couple to the noisy environment. And here I also added randomized compiling, which is also a compilation technique. It's a bit more complex, but it also plays with the idea that some noise, it's worse than other, to some extent, at least with respect to the error it induces on your quantum computation. And so here you see your original quantum circuit. And what you apply, as you see here, for each layer, you apply some additional gates. In specific, these gates have some properties. They basically shuffle the noise, and they tend to transform the noise into some other type of noise that is more amenable to mitigation. So in the end, you end up with a different quantum circuit that, generally speaking, from a logic point of view, perform the same computation, but in practical terms applies different gates than the original ones. And by doing this, this sort of like polytwirling, you hope to improve the situation by modifying the original noise. So in this case, you just try to decouple from original noise. In this case, as it's a bit more elaborate, you try to change the shape of the noise into something that is easier to correct by error mitigation. And remember, of course, there is other research with a mix of approaches or more specific approaches. So the transition has blocked. Let me see why. Yeah, so this is a slide. I will make this slide available for all, but if you want to take a picture or a screenshot, this is sort of like a minimal literature list divided by this topic. I think this stopped working, so I will use my computer. Let's see what's happening. Yeah, and more generally, here's one of the first reviews of quantum error correction that also includes hybrid quantum classical algorithms by Suguru Endo and other of his collaborators in Japan and in the UK. And all these references actually are present on the Mitic documentation. So that's where I took them from. Mitic is the software that I will speak about and on which we will have the lab session. So, yeah. Yeah, so I grouped it here under a symmetry-based technique, but I think it's more general. So read out, error mitigation, or post-selection. To some extent, I think if I were to group them, these techniques, they may in their own right have their own space, but possibly we could call them like symmetry-based techniques, I think. Yes. Oh, yeah, sorry. So the first question was, does post-selection fall under symmetry-based techniques? And I would say could stay in its own bucket, but it's definitely like the closest technique I can think. Set of techniques is this one, the symmetry-based techniques. Although in post-selection, generally you don't have this reprojection, but you just filter some results. The second question instead was, could you repeat the protocol for the learning-based for Clifford data regression? So in extreme synthesis, extreme summary, what you're doing is you're simulating your original hard quantum computation with a computation that is easier to implement classically. And then you simulate this also from a noisy perspective. Either you simulate it or you run, if you're available quantum computer, you send the computation to a quantum computer. And based on this training data, you build your model to then mitigate the errors on the actual hard computation. Because on the simple computation, you know what the result is because you're able to simulate it on your laptop or on your classical supercomputer. Yeah, I think it's one could say something like that. And actually, one of these papers. Oh, yeah, sorry. The question was, one could say that these learning-based methods are an expansion of the zero noise extrapolation. Yes, and actually, to some extent, they apply as you rightly pointed out, to many techniques. So one of these papers, I think this one, is actually a learning-based extension of probabilistic error cancellation, in which you learn the representation with this with a similar technique. And actually, Misty has been driving the efforts to port this technique into Mythic. And learning-based methods also have this Clifford data regression also has a variable noise sub-technique that also scales with respect to the noise, so also takes the idea, it borrows the idea from zero noise extrapolation. Yes, please.
How accurate in general is the idea, like how accurate is it to say that it's uncorrelated
Yeah. So the question is how accurate it is to assume that in current quantum computing devices, noise is a Markovian noise, which is a specific case as shown from the Markovian master equation, which I've shown. I would say it depends. It really depends, and you need to check. So I will also briefly comment on correlated noise and on some work that we've been doing to benchmark zero noise extrapolation against correlated noise. So I would really say it depends on your devices. What we could say is that generally one can imagine that some devices, such as superconducting circuits, can have non-Markovian effects that are more prominent than other devices that have an architecture such as ion-based or atom-based lattices. Why is that? Because atom-based and ion-based lattices are very similar to quantum optics experiments, and there's been like decades, well, now there's also decades of study in superconducting circuit devices, but decades of studies of how the excitation escapes from the system. And you can actually tell, like if you have a trapped atom and you have an excitation that escapes, which could be like a photon at a given frequency, the photon then escapes in the room. In the case of an artificial atom in solid state, you can imagine there may be like the photon is actually bound to stay into the waveguide. And so you can imagine that it could like sort of like be informed by, it could act as a cavity that is actually used to couple different qubits, but also with parts of the system that, let's say, you would like not to couple to, and then affect your device. Dynamical decoupling is particularly well poised to, well suited to correct non-Markovian noise because it's very general technique.
Sorry, does that just make the non-Markovian noise into Markovian noise by getting rid of correlations?
To some extent, you're trying to, sorry, the question is, does this technique try to make the non-Markovian noise Markovian noise? At first level, what I would say yes, because you're trying to decouple your system from the environment. Yeah. Thanks, that's a very good question. Other questions? Yeah. Yes, please. So the question is, if you don't have a system that can be simulated classically, can you still apply learning-based methods? So for Clifford data regression, it would be more difficult. But again, you start from a program that is not simulable classical and you modify it. So actually you're doing a sort of like a leap of faith is that you start from a quantum program in the programs that are easy to simulate, and then you infer that the things that you learn about noise and how to correct it will also apply to the original circuit. So the original quantum circuit is hard to simulate classically. And I would say this also applies to learning-based PC, because there actually what you're doing is you're simulating only at the gate level down even further. Does that it? Question from online, please feel free to ask. Otherwise, I will switch to zero noise extrapolation. Yeah, this stopped working, unfortunately. So, okay, thanks. Before moving forward, I also want to give a very high level workflow of what could happen to you if you try to more generally run a quantum simulation of a high energy physics model. And I think this is a framework that will really be adopted by many researchers, even if their field of expertise or interest is not error mitigation, just because these quantum computers are so noisy. So let's imagine that. Okay. Yeah. Yeah, and then if I go back, it's too common. Yeah, okay. So, yeah. So let's imagine that you have a problem of interest, such as the quantum simulation of a quantum field theory. You, for example, compile it into a version that is amenable to current quantum computers, such as a quantum circuit. For example, you trotterize your initial problem. This could be already a non-trivial task. And then you choose the best hardware and it's specific that fit your problem. This could already be sort of like hardware-based error mitigation, because let's say that you want to simulate a ZZ model and you implement it into a system that already has a ZZ gates to couple your system. Then you run on hardware with quantum error mitigation. And then at some point you may be interested in benchmarking and compare or just publish your results and hopefully open source the code and data. And this is what has been done by these researchers. This is a work by Emily Huffman and co-workers about real-time dynamics of plaquette models using NISQ hardware. This is the preprint. And as they said here, I'm reporting the abstract, the real-time, they want to simulate the real-time dynamics in strongly coupled lattice gauge theories, in which they have some frustration. They benchmark real-time dynamics of Z2 and U1 gauge invariant plaquette models using superconducting qubit-based quantum IBM-Q computers. So far, it's still this first part. And then they demonstrate the use of error mitigation techniques such as circuit folding methods, which is a subset of zero noise extrapolation, which I'll explain, implemented via the MITIC package, and show that what they can achieve within the quantum volume restrictions for the IBM-Q quantum computers. And here in this plot, you'll actually see that they show the simulated original unmitigated, so the simulated result, the original unmitigated, and then the mitigated result with a readout post-selection technique or a readout plus zero noise extrapolation approach that, as you can see, it's slightly closer to the noiseless simulation. Another high-level point before jumping into zero noise extrapolation, high-level framework for running programs on there's a quantum error mitigation in practice. What sort of like issues you may encounter? So, of course, you have your front end, which is how the framework in which you wrote your quantum program, your quantum circuit. You have a cloud, you access a cloud service, and then you have a backend provider. And nowadays, you can have all sorts of flavors. Here's just a limited list of these providers. Let's, for example, imagine that you use the Bracket Python software development kit. You access AWS cloud. You have some credits, hopefully, or you just use the free ones. And then you access the Rigetti QPU. But you could also access the IonQ QPU because, again, different cloud service providers offer different backends. Now, to apply error mitigation, you actually want to get rid, generally, of the sort of like advanced compilation features that these providers at some level apply. Yes, please. Yeah, and getting to the point. I mean, generally, it's not. So the question is how hard it is to combine different pieces of these different stacks and combine them. So I think it really depends, because from a user perspective, you may be used to code in one of these frameworks. That makes sense, and you want to keep things that way. So what I make, the case I'm making is that generally speaking, there are conversions among these different pieces of a stack. So you're able from any point to reach any point, but this is limited to, okay, these are basic contracts between the providers and the cloud service providers, the backend providers and cloud service providers. So not all services will have all backends. But then there's also a problem that not all languages or framework allow you to do the same thing on the backend specifications. Because, for example, for error mitigation, what you want to do is that you want to apply the error mitigation technique. So you want to have sort of like full compilation, because you want to apply with, for example, tools like Mitic, specific compilation of your quantum sequence. So you don't want something else to happen behind the scenes beyond your control. And not always you're able to do this step with any device. So for example, in one specific case, it's simpler to disable optimization in the compilation on IonQ quantum processing units if you access from the IonQ cloud. But there are paths to go there. So this, yeah, I hope this answers your question, but it's exactly to make this point. In practice, to apply quantum error mitigation, you have to find a path that is amenable to have low-level control from your side. And basically what this means is disable any sort of like sophistication that is done behind the scenes. Okay. I'm definitely late with respect to the schedule, but let's go into the in-depth look of zero noise extrapolation and also like mentioning Mitic. But maybe I can be a bit faster on this thanks to the lab session later on. Let's go back to this Markovian master equation formalism. And as you can see, and now we try to explain more in detail how zero noise extrapolation works. So you don't have this term. And basically this is the noiseless evolution that you want to implement. With lambda equal to 1, this is the sort of like hardware dynamics that one is experiencing on the hardware. As I briefly mentioned, what we can do is we can increase the noise. So we can implement this evolution with a greater noise interference with respect to this part of evolution. And how do the results look like? Well, they will look something like this. This is actually, I think, some data that Ryan took back in the days. So you see at noise scale factor lambda equal to 1, you have actually a result without applying any zero noise extrapolation. And then here you see that you have actually a worse and worse result, because in this case, we know that the expectation value should be 1. And so we are basically degrading progressively the quality of a result by increasing the noise scale factor. And I will show what we mean by increasing the noise scale factor. There are different techniques. Once you do this sampling, you're very simply able to do a curve fitting and extrapolate to the zero noise limit. Yes, question. So the question is, do you already need to characterize what noise level or model is? So to some extent, no, because this is a dimensional noise factor. So first of all, you don't need a priori a noise model. You can just empirically use the data that you obtain. And of course, the better you know the noise characteristic, the more effective can be your noise scaling protocols and also your inference protocols. Yes, that's the point. So with that respect, that's true. But you assume that you have like a noise scale factor equal to lambda equal to 1. So sorry. What you do with this respect, you calibrate with respect to a known expectation value first. That's the way you get around it. Correct me if I'm wrong, people in the room that are familiar with the technique, but that's the question. And the noise level, it's arbitrarily given up to 1. And what you can assume, and it's realistic, you are decreasing you increasing the noise scale factor by some protocols that you apply. What are these protocols? So in the first proposal, this theory paper, and then the actual implementation on hardware, what has been done, it's basically the sketch of the quantum circuit I shown in the previous slides. So they have stretched the pulses into longer time frames. You see it here. The same gates here. So each of these, it's a gate. This is a control knot. These are single qubit gates. It's implemented at the pulse level on the device, which is this superconducting device by IBM. And what they do, basically, they make the pulses longer. So you see that the same gates are applied, but they're on a longer time scale. And what they do, they start from this noise level, they obtain a higher noise level, and then they extract to the zero noise value. And this is again some experimental data from this first paper, in which here with the different colors, you see the different curves. And as you increase the survival probability of this quantity, by 0, which should be 1 in the ideal case, you see that even for deeper circuits, they were able to obtain results that were closer to the ideal one. So going from the bottom curve to the top curve, you see the improvement obtained through zero noise extrapolation. And here is also another way to depict it. And this is actually applied to a different, so this was applied to a single qubit expectation variable, I think, and this is applied to a 2-qubit expectation variable. Okay, let me go back. So let's get to Mythic, because we don't always have pulse level control to all devices. Yes. Yeah, but it's not working for some. Yes.
So this is all working on the level of expectation value, right? Is there any other implementation method you know, or similar things like on the level of a single corrective or single measurement?
So the question is, do you know, so this all works at the expectation value level. Do you know of mitigation techniques that work also at the output level? So I would say before doing the measurement. And this is like, from my perspective, generally, when we speak about error mitigation, it's with this constraint, which is a big constraint with respect to other quantum error correction techniques. And the only technique that I can think of is dynamical decoupling, which is in theory not limited to this expectation value. It's also true that with NISQ devices nowadays, you can, the only kind of computations that you can try to perform are these expectation value based calculations, even in the hybrid formalism of variational quantum algorithms. Yes, question.
This is because when we use any of these untitled systems, we decide
yeah, so the question is, when we use different quantum computing devices, do we have control to the compilation that occurs behind the scenes? Is that a question? Yeah, so that's what I was referring to in that big slides with the different front ends, cloud services, and backends. Different devices may have some limitations with respect to what API from the cloud is accessing them and what front-end framework one is using. So generally speaking, you can imagine that you have more features if you use, let's say, the standard tools that have been designed by the chip maker to use with the front end. But yes, the effort is to try to extend as much as possible this low-level compilation control. And to some extent, of course, providers want to already implement zero error mitigation techniques or compilation techniques or optimal control behind the scenes, also for calibration. But on our end, if we're interested in applying quantum error mitigation techniques, we want this compilation to be as much as possible disabled. So in some cases, I can think, for example, in Rigetti with Bracket, you can use an option called verbatim compilation, which means that you tend to know that the system is compiling just what you're sending. With IonQ, they recently provided this native gates control, but it's somewhat limited to what framework, what cloud service provider you use and what framework you use to code into the backend. Generally, for IBM, it's possible to set the optimization to 0. And yeah, generally you access IBM through the IBM Q experience. Question? Yes, so yeah, need to hurry up. So yeah, but if there are other questions, very good. Feel free to ask. So yeah, so this is Mythic, and we will have like a notebook online later on. But if you wish during the break, try to install Mythic. You just need to do pip install Mythic. And as it's a toolkit, including many different error mitigation techniques, some that we adapted or developed internally at Unitary Fund and with collaborators, and some are taken from the literature. It is compatible with many front ends that we've been speaking about, and it is designed to work on any backend by design. And the techniques, we refer to them with these acronyms. So more are actually present, but the most documented one right now are zero noise extrapolation, probabilistic error cancellation, Clifford data regression, and digital dynamical decoupling. And here you also see a sketch of the main divisions of Mythic. And besides these techniques and the more specific submodules, here you also see that we have some benchmarks. So we have some tooling to allow to run specific algorithms that are helpful to calibrate and benchmark your system and your error mitigation technique. They can be quantum volume circuits, GHZ circuits, randomized benchmarking circuits. And then there's also like a module for interface that actually simplifies going from one front end to the other in case you prefer to code your original quantum circuit in a specific framework. Because Mythic behind the scenes is using for its internals circ. And there's also a white paper at this link, which is currently on the archive, but it has recently been accepted in Quantum for publication. And as you can see here, there's more folks than those at Unitary Fund, and that's because it's been a community effort, and we're really thankful to all those that volunteered and contributed to the project, also beyond those that are acknowledged in the paper here. So once again, we've now become familiar with this sketch of a typical workflow in quantum software. And here, let me just plug in what is happening here. What Mythic means, yeah, what Mythic does. As we said, we generate many quantum programs, and then we apply an inference technique. And as you can see here from the acronyms, this first part refers to a different technique, and there is some sort of like scaling or sampling or training data that is applied. For dynamical decoupling, as we were mentioning, that's the full technique is in compiling differently the quantum circuit. But then there is also like different specific techniques for the inference that are applied at the classical level. So how do we do this noise scaling? This is something I want to cover before the end. And it's true that on some providers, you're now given pulse level access. So this is what happens with pulse stretching. Visually, you can imagine that you're making these quantum gates longer. But we devised some techniques that allow to scale the noise at the gate level, at the digital level, so without pulse level control. And here you can see two different approaches that we named local folding and global folding. So what does global folding do is, let's imagine that you have a gate here, G. When you do the noise scaling part of zero noise extrapolation, so you want to sample at a higher noise level, you make the quantum circuit longer by applying G dagger G instead of original G gate. And G dagger G, since these are unitaries, it's just the identity. So you know that this circuit is logically identical to this circuit. And the differences that you will see, if there is not further compilation behind the scenes, but it should be uniform for these cases, is just due to effect of noise. To some extent, this is working the contrary of a usual compiler. A compiler takes a long quantum circuit and tries to optimize generally for the number of some gates that are especially costly or noisy, but generally wants to make your quantum circuit shorter. So in this phase, we're using a compiler in the opposite way. What we call global folding is basically the same concept, but applied at the full quantum circuit level. So it's G, it's the full unitary that you're applying, and then you just apply the dagger, and then again, the full set of quantum gates. Why would you do one or the other? This is stuff that we've been testing on the field. And generally speaking, is you want to minimize impact of correlations or wash out correlations as much as possible. So we've seen some dependency on of noise with respect to what sort of folding technique you apply. And this also may apply, this also may have some effect with respect to the variational quantum algorithm that you use. I already mentioned this example of a paper made with Mitic. These are two other examples. So this is actually some mirror circuit, which is a sort of like a benchmarking quantum circuit run on Rigetti, again by Ryan, in which you see the lower curve, it's without error mitigation, with the higher curve, it's with error mitigation. And you see that for increasing depth, at some point you average out to a very low value, but at intermediate levels, you can have a really gain with respect to the original value. And in this case, always we're testing it on a benchmark in which we know that the expectation value should be 1. So these are decreasing in quality and fidelity, but this is decreasing more slowly than this curve. And here actually you see the net effect. So not only mirror circuits, one can also apply this to quantum volumes protocols. And this is another paper in which you see that what's been named an effective quantum volume benchmark has been increased with application of zero noise extrapolation, which is shown here with respect to the rho. So actually in this case, the quantum volume is increasing by 1, and quantum volume, for those of you that may not familiar, is just one of the many existing metrics that characterize quantum hardware. So this effective quantum volume, it's a modification of this original definition just for the hardware. So this kind of answers the previous question. How much do we can we expect that noise it's white and it's non-correlated. This is a recent archive paper we've been working on, applying, so the paper is nice because it puts together different tools. One is Mitic, and one is a tool developed at Johns Hopkins University called Shammah, which also uses some ARMA models, which come from the field of noise filtering, completely classical. And basically, it's a recipe to be able to know that one can model colored noise in a way that is physically consistent. So here you see, with a normalized frequency, different noise spectra that may be a property of environment affecting the quantum device. So white noise is this one, and then there's different kinds of like low pass filters, 1/f, pink noise, they have different names. But basically this is just to say that we benchmarked zero noise extrapolation with respect to these different color noise spectra, and also these different curves refer to different noise scaling techniques. So given, so different panels here refer to, so these two panels refer to different noise types, color noise types that are present, and then different protocols for noise scaling are employed. And here we see that there is some variability, and actually that global folding is the one that is promising the best gain with respect to different correlated noise levels. In this case, the first plot, this panel, I think, is just white noise. So you see that there is no difference between the different noise scaling techniques, whereas here these are different noise frequencies and spectra, and you see the different noise scaling techniques have an impact. So you will see more hands-on what it looks like to apply zero noise extrapolation with Mitic. This is just an anticipation of what it looks like. So you have your original circuit that you define here with a couple lines of code with your quantum circuit. This is the output. Is I just draw here what G looks like. You apply global folding with a given noise scale factor, and what you obtain as an output is this noise scaled quantum circuit. And we mentioned earlier the different noise scaling protocols. There is also different inference techniques that can be employed. So the one that through which zero noise extrapolation was devised is Richardson extrapolation. And but there are more general curve fitting basically techniques that one can use. And this is sort of like some low level control that you can have in Mitic. You don't necessarily need it in the example here, but we've put these techniques to test on real hardware, both on IBM Q and on Rigetti, and also to answer the question earlier. We've seen that different curve fitting were matching, depending on the device, the expected outcome. So for in case of Rigetti, it was not the exponential fit the best one, and we believe that it may be due to some non-Markovian noise that may be in place in the system. Okay, I basically have 5 minutes, I think, or yes, even less. Okay, so I will go very fast. I just want to acknowledge some things. So yeah, maybe you can ask me or ask us in person what All Unitary Fund is about. I spoke about Mitic and error mitigation and the active research we're doing. Unitary Fund is a nonprofit whose aim is to make the quantum technology ecosystem as open as possible. And to do so, we think that one of the ways that this is most efficient is by supporting and developing a robust open source software ecosystem. One way we do that is through these Unitary Fund microgrants. There's been many grants that have been awarded so far. These are very no strings attached, easy to apply microgrants for personal projects or team projects with a scope. They don't need to be in open source. They can also be community activities. but there's been quite an output in like a diverse pool of applicants. Now, I think now 23 countries. We're given the last microgrants to an applicant in South Africa. Then they also led to scientific publications, many libraries, and then even if this is sort of like personal projects or non-competitive projects, scientific projects, some of them have moved on to some more elaborate technology transfer. One project I want to mention is Metric, which is an online platform that you can find at metric.info. And it's basically a community-driven quantum computing benchmark platform. And we did mention a couple of times that you can have different workloads, apply different quantum error mitigation techniques, and apply on different backends. And all of these ends up with having different results. And it's very hard right now to get where the state of the art is. We definitely know that some metrics are more popular for hardware. We also think that error mitigation will be used to improve most metrics and to benchmark them. So it's kind of like crucial to be able to provide tools like Mitic to be able to apply easily error mitigation as add-on on different protocols that have been made. And so this is a typical page of Metric in which everyone can add a submission, which could be a paper from the archive, a GitHub repository that contains, I'm sorry for the low quality, but contains results, in this case, against log quantum volume, against time. And as you add a new paper and you by hand extract a result, this will be updated on the chart. So you're able to do your own chart, define your own task, your methods, and basically this is a community-driven approach that we are implementing. And I think it's a very useful way to browse the literature and stay up to date. And we're actively developing this repository. I don't have time to speak about the other things we do, but yeah, generally speaking, we support many open source projects such as QTIP, other projects with hackathons such as Unitary Hack. We have an active Discord channel. This is the team. So a couple of us are present today. And yeah, I really want to thank everyone. We have also 2 interns that are interning for the summer, helping on Metric. And then the Mitic team has been Ryan, Sarah, Peter, Will, myself, Nate, Misty, Andrea, and Vincent Russo. Finally, I also want to acknowledge the broader Unitary Fund community. So as you can see, Misty was also a Unitary Fund ambassador. So she transitioned from an enthusiastic and very effective volunteer in our community to a team member. So these are other team members that helped us achieve new additions to Mitic. We have a community of awardees. So once again, please go to unitary.fund if you have some idea that you would like to be funded. And these microgrants are evaluated by an advisory board. And yes, once again, this is just another example of a software tool developed by Steven Diadamo, which is a quantum network simulator called QNetSim. And then Steven became one of the advisors reviewing the microgrants. Okay, I think that's it. Other supporters are shown here, including SQMS. QTIP community we can skip, unfortunately. And let me just give the conclusions really fast so that you can read them as we leave. So basically, quantum error mitigation can improve the performance of quantum programs now with NISQ devices. It will be a critical component where benchmarking different solutions, even if your interest is not into quantum error mitigation research, which is a very dynamic and active field of research. It may have and seems to have applications beyond the NISQ era, as it can improve quantum error correction. And Mitic is a tool that is devised to allow everyone to implement these techniques. And something that I really briefly touched upon, but of course, Unitary Fund is part of SQMS, and SQMS is committed to supporting this quantum open source software ecosystem. So that's the last slide, and sorry for being a bit over time, and thank you for your attention.